you two champions, welcome to day 2 of 21 days challenge to get 95% in second PUC board exams. So in today's challenge, I have given you two chapters for homework. The first one was integrals from maths and the second one was chemical kinetics from chemistry. So you need to revise these two chapters and solve its most important questions from the PDF I have provided. Now, if you haven't downloaded the PDF yet, do not worry. The link is there in the description section. Click on the link, go to the page and download the PDF right now. Okay. And in this video, we are going to do a a quick rapid revision of the chapter Chemical Kinetics. And after watching this video, the entire concept will be clear to all of you. Okay, so let's get started and see what all topics we have in this particular chapter. So the first very important topic is the types of reaction. One second. Yes, the first important topic is type of reactions. Then we'll talk about the rate of a chemical reaction, factors affecting the rate, effect of concentration, effect of temperature, effect of catalyst, and lastly we'll talk about collision theory. Okay, so type of reactions, basically we have two types of reaction, like on the basis of number of steps. One is your elementary reaction and the other one is a complex reaction. Elementary reaction is that type of reaction which occurs in one step, whereas in complex reactions we have many steps, right? That is the basic difference. Now in a complex reaction, when there is so many steps, the rate of the reaction is determined with the slowest step. Okay, now, the rate of a chemical reaction, how do we define the rate of a chemical reaction? It is the change in concentration by the time taken. Now, this change in concentration can be for the change in concentration of reactants, can also be for the change in concentration of the products. If it is a reactant, then we use a negative sign with the reactant. And if you're doing with respect to product, you can see here this reaction A gives you B. So if I'm talking of the rate in terms of A will disappear, right? Because it is the reactant, it will get consumed with time. So it will be minus change in concentration of A by change in time. Now, if you are doing with respect to B, since it is a product, B will form with time, so it will have a positive value. Okay, now what will happen? You can see the graph here. The concentration of the reactant is decreasing, whereas the concentration of product is increasing with the time. Okay, now talking about the rate of a chemical reaction, the first one is average rate, instantaneous rate, differential rate equation, and unit of rate reaction. So these all four topics we will cover under rate of a chemical reaction. So what is average rate and what is instantaneous rate? See, a rate of a reaction is called as average rate if it is measured in a certain time interval. Okay, you have certain 10 minutes, 20 minutes, 1 hour, 2 hour, in certain time interval you are measuring. That is called as average rate and it is represented by the triangle delta value. Okay, now if you're talking about instantaneous rate, it is measured at that particular instant. Okay, at particular time you need to measure the rate of the reaction or the instantaneous reaction, and it is represented by d by dt. Now coming to the next one here is like this. You can see that we can calculate the for this the concentration is decreasing, the rate is decreasing. So here there is a tangent drawn there. Okay, you can see now in this particular graph I'll show you how we can calculate average as well as instantaneous rate. Okay, so now if you see here, if I take two particular intervals, this time interval and this time interval, okay, T1 and T2, in these two time interval the concentrations that I have is R1 and R2, right? This is the time interval and this is the time interval. So the change in concentration of R by the change in time is called as your average rate. And what is instantaneous rate? So if there is a particular curve, okay, and if you draw its tangent at that particular time, and if you have that one, then you will, if you draw the slope of this tangent, that will give you the instantaneous rate. This is for the reactant graph. If you have the product graph where the concentration is increasing, you have the same thing. You can see for T1 and T2, if you have taken P1 and P2, okay, and you can see the change in concentration here, that will be P2 minus P1 by T2 minus T1. And here, if in the graph you draw the tangent here, okay, and the slope of that tangent, if you calculate, that will give you instantaneous rate of the reaction. Now, how to get the differential rate of a reaction? So if you have a reaction like this, okay, how can we write its differential equation? So rate will be equal to, since these are reactants, with that I will use a negative sign, okay, and the coefficients of the reactions will be divided. So minus 1 by A dA by dt, here minus 1 by B dB by dt, and here since C is formed, so plus 1 by C dC by dt and plus 1 by D dd by dt. Okay, now we'll talk about unit of rate. So as you have seen, rate, I'll change the color, just a minute. Now if you see, rate is what? Rate is equal to nothing but change in concentration by change in time. Okay, and concentration we generally take in terms of molarity. So mole liter inverse and time will be second inverse. Now if you have taken gaseous thing, then the concentration will be in terms of pressure. So we will have pressure unit, which is atm, and second inverse. Okay, now let's talk about the factors affecting the rate of the reaction. The first factor is concentration. As the concentration increases, the rate increases. The second factor is temperature. As the temperature increases, rate increases. Nature of the reactant. Okay, what is the bonding in between the reactants? If the reactant is having very strong bonds, then the rate will be slower. Then catalyst also increases the rate of the reaction by providing an alternative pathway and decreasing the activation energy. What is this activation energy and all? We'll see at the next slides. Surface area. More is the surface area, faster is the reaction. Radiation. If the reaction involves photochemical reactions, we need light energy. In that case, radiation will also affect the rate of the reaction. Now talking about the effect of concentration, the first one here we have is the rate law and rate constant, order and molecularity, integrated rate equation, half-life, and pseudo first order reaction. These are the topics we will cover under effect of concentration. So what is rate law? Rate law is nothing but it is an equation. It is an equation that relates the rate with the concentration of the reactants. Okay, now you can see here, suppose any reaction is there, A gives you B, then for that the rate law is equal to, so rate is basically proportional to the concentration of A and concentration of B. Okay, to remove that proportionality, we multiply this K, which is called as your rate constant. Okay, and this X and Y are order of the reaction. X is the order with respect to A and Y is the order with respect to B. And what is this square brackets denote? It denotes the molar concentration of the reactants. Now moving to the next one, what is this rate constant? How will you define it? So the value of rate constant K is equal to the rate of the reaction when the concentration of each reactant is unit. If this is 1 molar, this is 1 molar, at that time whatever is the rate of the reaction, that is equal to the rate constant. Next, we'll talk about order and molecularity. There are some points of difference that you should know because this question has been asked again and again. Order, what is its definition? Sum of the powers of the concentration term. Molecularity is the number of species reacting in the reaction. Next, it can be zero, fractional, or even an integer. This can only be a whole number. Next, it is determined experimentally and it is determined theoretically. Applicability, applicable to both elementary and complex reactions. It is only applicable for elementary reactions. This can be 0 and this cannot be 0. We have already discussed that. Next, what is integrated rate equation? See, integrated rate equation tells you that suppose a reaction is first order. We know that it is a first order reaction. So suppose you have started the reaction and you have passed some time, 10 minutes, 20 minutes. So after 20 minutes, what is the concentration? To find out that, we need integrated rate equation where there is a function of concentration and time. Okay, or let me give you another example. Suppose you have started with 10 moles of reactant A and you want the A to come to 7 moles. Okay, so how much time will be required for this reaction to happen? If you want to calculate that time, then also we need integrated rate equation. Okay, so differential rate law, if you do calculus, that means if you integrate the differential rate law, we get integrated rate law. So integrated rate law for 0th order derivation is important. I have already explained this. I will explain this derivation in the most important question video. You can watch that. But here also let me just tell you. So R gives you P. Suppose this is the reaction. Rate is equal to minus dr by dt is equal to K into R naught, right? So now if I just integrate this one, then I'll get R is equal to minus KT plus I. Then to find the value of I, you have to consider R equal to R0 and T equal to 0. Now substituting this one, I'll get I equal to R naught and then just solve all this and you will get R is equal to minus KT plus R naught. Okay. Next, we'll talk about the integrated rate equation for 0th order graph. Okay, so you can see here, this is the equation R naught minus R is equal to KT. Okay, so what is the concentration of R here? R is equal to minus KT plus R naught. Okay, now Y is equal to mx plus C. So what is the slope here? Minus m minus k, and C value is R naught. So since there is a negative slope, the graph will start from, we'll have a negative slope like this. Okay. Now examples of this one, there is a very famous example. Surface catalyzed reactions are generally 0th order reaction. One is decomposition of ammonia. Okay. So why it is a first 0th order reaction? So basically what happens, the surface is there, right? How much, suppose this is a surface and here we have suppose 5 spaces or 6 spaces. Now when already the 6 ammonia molecules are filled here. Okay, after that, even if you increase the concentration of ammonia, the reaction will not take place because we have only these 6 places, right? So that is why in such type of surface catalyzed reactions, the what I can say, the rate is not affected by the concentration. Now moving to the next one, integrated rate equation. We'll talk about the first order derivation. So here also R gives you P, suppose this is the reaction, minus dr by dt is equal to kr, then you can multiply R on this side and then integrating on both sides you will get this value. Then to find the value of I, you have to take t equal to 0 and R is equal to R naught, and then calculate this one and you will finally get this integrated rate equation. Okay, next is for the graph. You can see these are the graphs for I can say graph for first order reaction. Ln, this is for ln R versus T, log R naught by R versus T. This will pass through the origin. This is important. This graph is also important. Examples of first order reaction: hydrogenation of ethene. All natural and radioactive decays are your first order reaction. Decomposition of N2O5 and N2O are also first order reactions. Now here there's a summary table. You can see for zeroth order reaction, we'll have the integrated equation Kt equal to R naught minus R, and if you plot R versus T, it is a straight line. The half-life value is R naught by 2k, and what is half-life we will discuss, and the unit of rate constant is for zeroth order concentration time inverse. Okay, that is mole liter inverse second inverse. Next, for first order, R gives you P, we have minus k into R, and here the equation is Kt is equal to ln of R naught by R, or I can write k equal to 2.303 by T log of R naught by R. Okay, next we have half-life ln2 by k, and it is time inverse or second inverse. Now we'll talk about what is half-life. So half-life is the time that is required for the reactant to get reduced to half of its initial concentration. Means suppose you have started with 50 moles, the time required to come to 25 moles, that is half-life. If you have started with 12 moles, the time required to come to 6 moles, that is half-life. Okay, so half-life, for half-life what you have to calculate, so you have to just change the substitute T equal to T half and A or A to A naught by 2, and then if you put it in the zeroth order integrated equation and first order integrated equation, you will see T half is equal to A naught by 2k. For zeroth order, it depends on the initial concentration, and for first order it is 0.693 by k. It is constant and independent of the initial concentration. Okay, next, what is pseudo first order reaction? Here this is important. See, a pseudo first order reaction will have two reactants. Okay, it is actually a second order reaction, but it appears to be first order. Now what is the reason behind it? One of the reactant is present in excess. Now when one of the reactant is present in excess, if you remove it some from it, or if you add some of that reactant, it does not really change the rate of the reaction. So even though we have two reactants, one is so much in excess that even if you change its concentration, it doesn't affect the rate of the reaction, right? So that means in affecting the rate of the reaction, it has no role. So only the first reactant concentration will affect. So that is why it is the first order reaction. Example here is hydrolysis of ethyl acetate and inversion of cane sugar. Okay, two examples are given. Next, we'll see about effect of temperature. For a chemical reaction with rise in temperature by 10 degrees Celsius, the rate of constant is nearly doubled. Okay, so we have Arrhenius equation and Boltzmann curve. So we'll discuss these two. So in Arrhenius equation, it tells you that temperature dependence of the rate of a chemical reaction can be accurately explained by the Arrhenius equation. Means when the temperature changes, how the rate will change, that will be affected by Arrhenius equation. You have k equal to a into e to the power of minus ea by rt, and here we can write down all the terms. Okay, so you know all the terms here. A is what? Pre-exponential factor. Okay, A is pre-exponential factor. EA is activation energy. Okay, then R is gas constant, and T is your temperature in Kelvin. Okay, now what will happen? So what is Arrhenius theory tells us that when the reactants are reacting to give you products, they're actually not directly converted into products, rather they are first converted to an activated complex or an intermediate complex, and this is converted to the product first. Okay, so now if I see, we have this graph for the Arrhenius equation, ln k is equal to ln a minus ea by rt. So you can draw the graph for this one. This is y, okay, this is m, x, and this is c. So here you can see this is y-axis where we have this particular intercept. Okay, this one ln A is the intercept here. Now if you see here, minus EA by R is the slope, and from that we can calculate the activation energy. Next, for two different temperatures, this from here numericals are mostly R. So log of K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Okay, so this is the formula for two different temperatures. Next, we'll talk about Boltzmann curve. So Boltzmann curve gives us the distribution of the fraction of molecules and their energy. There is one point called as most probable kinetic energy. It is that value of energy where the maximum majority of the molecules have one particular energy value, that is your most probable kinetic energy. Now when you increase the temperature and when you decrease the temperature, so what you can see here is, now you see that all the molecules will not get converted to products, only those molecules, activation energy, okay, only those molecules which have energy more than the activation energy, they will be converted to products, right? This one only will get converted to product. So we have only these many molecules having energy greater than the activation energy at temperature T. Okay. Now at temperature T plus 10, what will happen? The number of particles having energy more than the activation energy increases. Okay. Now here number of particles having energy more than the activation energy increases, and that is why the rate of the reaction increases. Now coming to the effect of catalyst here. So catalyst is a substance which increases the rate of the reaction without itself undergoing any permanent change. Okay. So catalyst will remain as it is in the reaction. It just helps us to speed up the reaction. How does it do that? It provides an alternative pathway for the reaction mechanism by reducing the activation energy. Okay. And it does not change the Gibbs free energy or even the equilibrium constant. You can see this graph is very, very important. So if you see here what happens, just a minute, huh? So you can see that this catalyst, when you have without catalyst, this is the activation energy, and with catalyst, this is the activation energy. Now why this activation energy is so important? If you see Arrhenius equation, we have K is equal to A into e to the power of minus EA by RT. So I'll write here minus EA by RT. So I can just write it like A into A divided by e to the power of EA by RT, right? Now what happens when the uh, activation energy decreases? Okay, this whole fraction will decrease. So e to the power of that smaller number, that whole fraction will decrease, and if this value decreases, then the K value increases. Okay. Now we have collision theory here. According to this theory, what happens? The reactant molecules are assumed to be hard spheres, and the reaction is postulated to occur when the molecules will collide with each other. So reaction collision theory tells that how the reaction takes place. It can take place only when two molecules will collide, and they consider that the reactant molecules are in the spherical shape. Okay, and the number of collisions per second per unit volume is called as collision frequency and is denoted by Z. Okay, and another factor which affects the collision is your activation energy. So collision theory says that reaction happens when two molecules collide, but all collisions cannot lead to product formation. There is a specific criteria for two collisions to happen. Okay, the first very important criteria is your energy barrier, and the second one is the orientation factor. Okay, they should have enough amount of activation energy, and they should be properly oriented to be called as an effective collision. Okay, so this I have explained in much more detail. Orientation barrier means, suppose if you see for a reaction to happen, they must collide in this way. So if they collide in this way, only the reaction can happen. If any other direction they are colliding, reaction will not take place. Similarly, in energy barrier, the reactions must collide in such a way that the energy is more than the activation energy. Okay, so this is all about collision theory, and children, I have explained this chapter in much detail, and I hope this is clear to all of you. Okay, this was a quick revision. After this, a most important questions video with solutions will be coming. So do watch that and practice all the questions from that video. Then this chapter will be entirely done for the final board exams. Okay, so all the best, and let me know about the challenge. Have you started, progressed or not? So all the best, and like just keep working hard. Few days are left, right? So please put all your efforts. Okay, thank you so much, and all the best once again.